This program is brought to you by AGNES SCOTT College. For more information about AGNES SCOTT College, please visit our website at agnescott.edu.
So thank you for coming. Thank you for supporting the ACME lecture series. And we've got a fabulous talk today by Dr. Amy Sullivan. I'm just going to give you a little background because Amy Sullivan has, well, a fantastic career. So we have to tell you some things. She was an undergraduate at Bates College, where she was a physics major and a German minor. She did her graduate studies at the University of Colorado and was sponsored by the National Science Foundation. She's also worked in industry, doing display technology research, liquid crystal displays. Did I say that right? No, that's Display Tech was the company, sorry. She was doing research on liquid crystal displays for video cameras, and she's been designing and building lasers for Coherent. She's now been here just less than a year, is that right? As a Clairbout Luce. Thank you. Assistant professor of physics. We're very excited for that. And since she's been here, she has recently had a paper accepted to the journal Science, which is amazing. For those of you who don't know, that is probably the most prestigious peer-reviewed journal in science, in the discipline of science, in the world. So not just in the country. So that is. And
there are other countries.
There are a few other countries, and today, and she's also been invited to speak at the Optical Society of America, the annual meeting. She's invited there. Usually, to be invited there, you're one of the fellows at the Optical Society of America. So that was another amazing thing. So today, I think we're in for a treat. She's going to talk about her research. Beyond the microscope, 3D imaging without lenses. So let's welcome Amy. Thank you.
Thank you. So I thought I wouldn't have to do this because I don't have to do this in class, but I have demos and those people in the back of the room are not going to be able to see them. So you're all going to have to stand up and walk forward and sit in the front of the room. You were in the back. This also means you are not allowed to fall asleep during my talk. For those of you who are up all night, maybe you should stay in the back. So the problem is that physicists look at really small things, and so I can't bring big things in that you could see from far away. So we're just going to have to go with the whole small thing. All right, so now I think we're remotely settled. So the title of my talk, as Sarah said, is Beyond the Microscope, 3D Imaging Without Lenses. That's what I said I was going to talk about. That's not what I'm going to talk about. This is an April Fool's talk. So I am going to talk about that a little bit. But first I want to motivate. So I'm going to talk about a microscope. And many of you know what microscopes do, and there's lots of microscopes in the world. And so maybe it's important to motivate why I thought I needed to invent a new one, since the biologists have like 30,000 different types that can see pretty much everything. It turns out they can, except what I was looking at. And so I'm going to talk also about integrated optics. And so I want to start out by motivating what integrated optics is and why you might want to care. You might not want to care, I don't know. So this is a typical optical table. It's generally 8 feet long, 4 feet wide. It weighs about 1,000 pounds. It's usually on legs that are floating. And the research that we can do on optical tables is phenomenal. We can do microscopy that doctors would just drool over. We can do telecommunication signals at data rates that you would just be astounded by and you don't have in your house. We can do all sorts of really cool things. We can do remote sensing. We can do atmospheric sensing. And we can do all these things on this optical table. And we do all this research in the lab, and it's cool. And then we write papers about it, and then no one ever uses it because it requires a big optical table. So that's bad. So what integrated optics means is I'm going to take a big optical table, and I'm going to put it in a package that you can bring home with you and use. I'm not really that far yet, but maybe we could like bring it into a hospital and they could pay $50,000 and we could do new science, and that would be cool. So I want to show you some of the ways that people already do this, and why ours is better. So here is one of the ways. This is a laser system that I built. It's now, these are an inch apart, so it's about 9 inches by 5 inches by 6 inches. This is a really, really, really state-of-the-art laser system used for laser radar. So you can do atmospheric measurements for this. You can measure things that are vibrating 100 kilometers away with this laser. It is phenomenal. Obviously, well, maybe it's not obvious, but the government paid for this so that they can look at things that are really far away, and they can look at, say, I don't know, tanks. And you can see whether it's our tank or somebody else's tank just by the vibration frequency. So this is really cool. This laser here, I built it. It took me about a year, and it cost the government about $350,000. So you're probably not going to put that in your house. This was only a couple years ago. This is state of the art. This is the best we can do to take all of the functionality of this optics table and make it smaller in a compact thing. And we can take this and we can put it on an airplane, and that's cool. But there's no way that we're going to be able to use these things for that kind of prices. So what other people do? Because if this is an interesting problem, other people are working on it. Well, first we should probably talk about what it is they're trying to do. I want to take the optic table and I want to make it small, because small is better than big. Optic table's heavy. I want to make it cheap. None of us have money. We have less now than we used to, so we want things to be cheap. We also want it to be easy to manufacture. So that means we can make thousands of these. Like, for instance, we can do this in electronics, right? We all have a computer. We can do things that are cool on a computer. What I think is the epitome of things that we can do on electronics, here's an iPhone. Works as my computer. I can check the internet. I can make phone calls. I can play games. I can send pictures. I can take pictures. And it's little. And I'm guessing they sold thousands and thousands and thousands of these, maybe millions. And while it's not really cheap, it's cheap enough that I can have one in my pocket. We can't do that yet with optics. And there's a reason for that. So electronics are all made out of, say, semiconductor materials and metals. Turns out that you can grow all semiconductor materials and metals from much the same sort of manufacturing process. They're all made out of the same materials. And so it's easy. You send, now the semiconductor people probably don't think this is easy, but it's cheap now, so it must be easy. You can make things out of these materials really, really easily and really cheaply. In optics, we don't use metals. We use glass. Oh wait, we do use semiconductors. I have a semiconductor laser in here. We use crystals. We use magnetics. We send acoustic waves through crystals. We use lots and lots of different materials. And if we want to have all that functionality, we need to keep the materials. We need to be able to have a system that's really hybrid, that we can use anything we want from our optical table and put it in our little package. So that's problem number one. Problem number two is wires. So electrical wires are great. You take a piece of metal and you touch it to another piece of metal, and all the electrons flow. It turns out optics doesn't work that way. So electricity wants to go it doesn't want to go in a straight line. It wants to go the easiest path. So you can see lightning will actually sort of look all jagged through the sky because it's taking the easiest path. It'll find a piece of metal and it'll go to ground. And it'll find its own routes. Laser beams go straight. And if you want them to go crooked, they won't. They just go straight. And so we need to use optical wires. And these are the things I'm going to talk about a lot today. And these are optical waveguides. And so what we do is we trap light in these fibers, and we can send them around corners and things because they're trapped. But then we need to align some optical wire to some other optical wire. And for metal, we touch them together. Everything's happy. For optics, you have to line them up. And if you're off by about a micron, so that's, like, I don't know, 1/10 or 100th of my fingernail. So if I'm off by that distance, I lose all of my light. I don't get any signals going through. And if we lose all of our light in optical communications, does anyone know what happens when we lose all of our light in optical communications? It's bad. Our internet doesn't work. So this is important for that too. So our tolerances are really, really tight. And tight tolerances are easy in semiconductors, but not this tight, it turns out. They really can't do that well very cheaply. So one solution to this problem is use silicon. Silicon is the same semiconductor material that we use for electronics. It's use the same material and do optics in it. And they do cool stuff. This whole thing has got a little beam that goes through here. It splits up, it's got mirrors, it's very cool, and it's all about 40 microns big, it's tiny. And this is state of the art. This was presented at a conference a couple years ago. And the only thing it involved is a laser beam and a mirror turning a corner. And that's state of the art. That's one of the things we can do with this. Another thing we can do with this is we can make these kind of waveguides. This is a little guiding light. This is an optical wire. And we can make circle resonators. Turns out, I'm not going to explain this, but you can do all sorts of really cool things just by sending light in a circle. But it's still all silicon. The only thing that we've been able to incorporate here is silicon. And so we haven't been able to incorporate all the really cool things we've learned on the optics table into the manufacturing process. But it's cheap and fast. So we lose one, we get the other. The other way to do this is really just a smaller version of the laser I showed you. People take these optical fibers, and they put them in these little tiny grooves, and they line them up, and then they build these benches. And there's this little optical fiber, and then there's this little optical component, and another little one. And the way they align this is somebody sits there with a magnifying glass and tweezers and a whole bunch of electronics equipment that probably costs $500,000, and they align it, and then they glue it. This is also state of the art. So, but I'm not kidding. I mean, these are really cool things that they're presenting in conferences. And so we're not there yet. We'd really like to be able to put these optic systems in a package, and we just can't do it yet. So we have a crazy new idea. Doesn't work yet, but it's going to someday. So we're going to start over. We're going to say, let's throw out everything we already know, and let's actually try to get my optics table into a little package. So here's a piece of glass. I'm just going to start with a piece of glass. This is my new optics table, only it's small. And on this piece of glass, I'm going to put everything I want. So these are supposed to be optical fibers. And so that means I have light coming in and light going out. We're probably going to want to connect things like my computer wants to be connected to other computers. Intel is actually interested in these sort of connections for computer backplanes as well. But I'm going to need some signals coming in and out just for like electronics. And this is my black box. And my black box has anything I want in it. It could have a laser. It could have a spectroscopy measurement of certain chemicals. This thing could be used, people build little systems so that I can bring it out into, say, big crowds. And it'll be able to detect what chemicals are in the air to see if there's any chemical weapons being used. This could be an acousto-optical machine with acoustic waves and optics going through it, which would be cool. It could be crystals. It could be magnets. But we just put everything we want on my system. And then I cover it up with a photopolymer. So a photopolymer, and I'm not a chemist, so I'm going to give a very bad description of photopolymer. But the easiest way I can describe a photopolymer is it's just like a 5-minute epoxy. So you take two components, and you mix them together, and it's a liquid. And you pour it over everything. Just pour it over all your stuff. And it sets up, and it glues everything in place. So now I have a system where everything's in place somewhere, and it has everything I want. And then I come back, and I scan with some sort of a microscope. And I try to figure out where everything is. I say, OK, well, I said alignment's going to be important, right? So I need to find my optical fiber. So where is my optical fiber? So I'm going to scan in 3D, and I'm going to make a map of where everything is. Not where I wanted it to be, because we all know, anyone who's done experiments, that things are never where you want them to be. We find out where they actually are. And now all I would have to do, in theory, right, I have my whole optical system, is all I have to do is take this laser that's coming out of this fiber and connect it to that. And then maybe connect it over here. So that sounds easy. That's what we'll talk the rest of the talk about. We can do that. So the other cool thing about this material, it's not really like a 5-minute epoxy, is if you shine a green laser, exactly this color, into the material, and you focus it down to a spot, wherever the light hits the material, some chemical reaction happens, and the material becomes more dense. So it just becomes more dense where the laser hits it. And it turns out that all you need to trap light is to put it in an area that's really dense, surrounded by less dense. So you make this change in the material, focus the laser, and you just drag it. And now I have what we would call an optical waveguide. So this density change is called an index of refraction change. So I have a higher index of refraction in the material where I shine my laser. Then I put it out in room light, quite literally. I make all the rest of the chemical reaction happen slowly. We'll talk a little bit more about that. And now I have a system. My system's not sensitive to light anymore. It has everything I ever wanted in it. It doesn't have any alignment tolerances. And I didn't align it. This was all done with a computer. And that's going to be the important part here. If I had to sit here, of course, and align these and find them individually and draw these dots, which is sort of where we are right now, this is not effective. But hopefully, this will all be done with a computer. So this is the pipe dream. We're not there yet, but we can do some cool stuff. So I want to talk a little bit more about the material. So why are photopolymers cool? They act like a glue, so they adhere to everything. They have low cure stress. That means when the glue cures, it doesn't put stress on everything, and because that would sort of break and crack things. But it still remains flexible. It's actually like this rubbery material. It's also really sensitive to light. So this is fantastic. They do similar type waveguides using femtosecond lasers. So that's about a $500,000 laser system on a giant optical table that's so scary that most people don't want to be in the room with it. We can do it with a laser pointer. Just this level of power. It actually takes about 1/100th of this level of power to make those. And this is not dangerous for those of you who are in the audience and scared. And it's very sensitive, so we can actually draw, in addition to these waveguides, we can draw lenses in there, we can make holograms, we can do all sorts of cool stuff. So, now that I've talked, I'm going to tell you what I'm going to talk about. So the first thing I want to talk about is, how do these photopolymers work, just so we understand a little bit more about what's going on. How do we make these circuits, other than pretty drawings on the board? And then, how do we measure them? And this is one of the biggest problems we had is, it turns out whenever you make something new, you have to measure it so that you can tell people what it looks like. And that was very hard. And then if I have time, which I probably won't, I have some pretty pictures at the end about waveguides and what else I'm going to be doing. So first, we're going to do photopolymers. This is my very, very technical description of photopolymer. This is my material. These are glass slides. This is what the samples look like. This is glass slides with photopolymer in it. So this is about the size that we're talking about. This is big by most people's standards in optics, but it works. So I'm not a chemist, again. There are 2 chemicals in the photopolymer. There's probably more, but there's 2 I care about. There's the little circles and the big circles. The little circles are the photoinitiators. And so basically what that means is they absorb light, and then they initiate some chemical reaction. So they start everything off. And then we have the monomer. And the monomer join together, and then when you get lots of monomer, you get polymer chains. For those of you who aren't very familiar with what a polymer is, it's just a plastic. We start out with a liquid, it joins together in chains, and we get a plastic. So that's all we're going to be doing here. So now I'm going to shine some light on my polymer, just in a single spot, not everywhere. And wherever the light hits, I'm going to excite my photoinitiator. It's going to be in some high energy state, and it's going to run around and start a chemical reaction. And it's going to join up with the monomer. And eventually, it's going to run out because it's kind of empty here now, and it doesn't have any other monomer. So the rest of them are going to start to diffuse in and join up. And this process continues and continues. This can last for about minutes. And so what I end up with in the end is I end up with this area where the light was, where it's really, really densely packed, right? I've got lots and lots of material there, and it's not very densely packed in the outside. So now I flood cure the whole sample, and I have the rest of the chemical reaction go on. And what I end up with is right where the laser beam was, I end up with a higher density or a higher index of refraction. And so if this was now, it looks like this, but it came out of the board, a big long line, I could send light down that. Because light would be trapped in this higher density material. So now we're going to talk about how we do that. I want to show you the system we use. So this is fairly complicated for someone who's never seen an optical system. I've got a red laser and a green laser. The green looks like this laser pointer, and the red looks a lot like the lasers we have in the lab. So these are pretty cheap components. So let's look at the red system first. The material is not sensitive to red light. So if you shine red light on the material, nothing happens. All the things I just talked about, nothing happens. So I'm going to shine a red laser through here. And I've got a little optical fiber here embedded in the material, because I said we could embed stuff and connect dots. And I'm going to scan I'm going to take this piece of material. This is my sample. It's pretty big. It's about the size that I just showed you. And I'm going to scan it in 3 dimensions on some really nice high precision stages. Well, it turns out that if you got red laser, you got your red laser, it goes up here, goes over here, and focuses down. Whenever the focus hits a different material, so some sort of material change, so glass air, that would be a material change, I get a reflection. And the light comes all the way back through here, and over here, and through this pinhole. And I see a spot on my detector. So let's see what happens when I scan in, this would be my Z direction. So I'm going to scan, and what I get is wherever the fiber is, I see a blip. Wherever the glass polymer is, I see a blip, and then I get a big blip actually on the glass hair. So now just by scanning this red laser through on my detector, I know where everything is in 1 dimension. But there's 2 more. And it turns out that these we thought were going to be hard are really, really easy. So optical fibers, I told you, guide light. So light goes down, you can trap it. So if I scan this beam past this fiber, the light gets trapped in it. And so I can just see whenever the light goes into the fiber, and then it must be aligned. So let's scan. I scan across, and I get this nice big signal where my optical fiber is. And so now I found it in 3 dimensions. Just by scanning around with a very simple, this is also called a microscope. It's a different type of microscope, but it's very simple. I've actually drawn out all the optical components. This is what the bench would look like. It has some lenses and a couple pieces of glass, and that's about it. So this is the system. You probably can't see too well, but this is my big optical bench. And I made the red go away, so it's less confusing. And now I've got a green laser. So I know where the fiber is, and now I want to draw a waveguide off of it. So I start with the shutter closed, because the material is sensitive to green light, and I don't want to do anything when I don't want to. So we open the shutter, and this lens focuses the beam down somewhere behind the fiber. So it's hard to, the way we draw this, it's hard to tell, but when I focus a laser down, and not very sharply, just pretty loosely focus it down to a spot, what I end up with, even at these very small lenses, is about a million times more intensity at the focus than I had here. And so it's the intensity that's making this process happen. So it's really only this little tiny focus is making anything happen at all, because it's so intense. So I then start out with this, and then I scan as I did before. And then I close the shutter, and I get an index change, and I make my waveguide. So I have, if it works, I have a little movie that's happening. So this is my lens, this lens right here. And I'm focusing down some light, and I move it. So I basically open the shutter, focus the beam, and move the part through the beam. This is about the speed we do it at, and that's just a sample writing. I have the power turned up a little bit high so that for the camera, but that's pretty much what this looks like. I spent many years watching that happen. So now we've got a waveguide, and now we get to the hard part that we'll probably talk about for a long time now. So what did I just do? I made a waveguide. Cool. What does it look like? So these things are small. We're talking sort of micron scale objects. Again, you know, 10th hundredth of my fingernail thickness. They're very small, and the density changes are about 1/10 of 1%. So very, very, very small. So the first thing we did, we said, well, we need to measure this, so we'll use a microscope. Everyone knows how to use microscopes. Well, if you give this big, thick sample to any standard biologist and say, can you put this under my microscope? They say, sure, it's kind of big. So you have to cut it up. And you have to make a really thin sample for the microscope. We said, okay, well, we'll do that. Well, this actually took a really long time because it's rubber. And if you try to slice off a 10-micron slice of rubber, it doesn't work. Months and months of trying, let me tell you, it doesn't work. So what you get to do is you embed it in this material, and you freeze it down to -20 degrees C, where it turns into more of a glassy material, and then you cut it. This is fun. I had a lot of really, really nice biologists help me out with this project. I gave up lots of their time and equipment. It was fantastic. So I end up with these little tiny slices of polymer on a microscope slide. And then we put some oil in a cover slip, and we look under a microscope. This is really nice, state-of-the-art. differential interference contrast microscope. It's very cool. And we get some pictures. All right, so let me tell you what you're looking at. So my waveguides are long, right? I want light to go down a waveguide. So this is just a cross-section. So I have a round waveguide, and this is nice and round, and it's coming straight out of the board. The light would be going down the waveguide. The reason I have 3 waveguides here. The reason I have 3 is because trying to find one in a big sample is impossible. Trying to find a set of a bunch of them is easy. So we did that. And this is sort of what we expected it to look like. So we're not so bad. This is not a great picture. It's sort of qualitatively, it looks kind of round, and there's something in there, and that's cool. We were very excited about that. We also proved that you can send light down it. You can send light down the waveguide, and it comes back out, and it couples in, and you don't lose a lot of light, and that was very cool. And we also measured, this is the index of refraction change, so the density change. It's 3 times 10 to the minus 4 in change, so that's maybe 1/100 of 1% change, which is perfect. That's exactly what we wanted. So we've done a little bit of measurements here. Unfortunately, if you want to say, I have this new manufacturing process and we should all switch to it, people want to know, well, okay, but we want more information. What do the waveguides look like? And what happens when you do this? And what happens when you do this? And we don't know. So one of the main problems here is we have to cut it up. That was bad. And this is a qualitative picture. We can't actually get quantitative information out of it. This type of microscopy just doesn't give you quantitative information. So I can show you a picture and say, look, it's pretty, and that's it. That's all we can get out of this. And your eye is very, very sensitive. So if you try to scan across that and draw some data, draw a data line cross-section across that, it looks like noise. It's amazing what our eyes can pick out. So there's not much information here, but it's a good start. So now I'm going to talk about some imaging. That's what I promised I'd talk about, I think, so we should probably get there eventually. So why is this hard? So I told you a couple of the reasons. Small. I want to look at small things. Microscopes can look at small things. I want to look at very weak things. Microscopes can't look at weak things very well. And when you add small and weak together, just absolutely impossible. They laughed at me. Every time I would go to a microscopist and say, I want to look at this, they'd just laugh at me. And it's also deep. I don't want to have to cut these things up. I want true 3D circuits. I want a big hunk of polymer with stuff in it and waveguides. And you can't do that with standard microscopes. And they're really 3D. I want 3-dimensional images. I don't want just 2D cross-sections. All right. So there's a couple ways of doing this. The one I showed you already, and we have some pretty gray pictures here. It's very good qualitatively. It's not very sensitive. People are still working on this. You still need to cut it up. It doesn't work. There was that scanning microscope I showed you at the beginning, that red one. We scan around and look at stuff. Turns out it's really sensitive to sharp changes. So if I've got glass and then air, it'll find that right away. If I have things that kind of slowly vary and go back and no sharp edges, I can't see them at all. And that's just how the microscope works. So I'm going to talk, eventually, about something called optical diffraction tomography. So I'm going to start out with the greatest website on earth, How Stuff Works. And I'd like to explain to you how CAT scans work first. So most people have at least heard of a CAT scan. CAT scan stands for Computed Axial Tomography. So it's the same thing, tomography, that we're doing. It's just a little bit different. So if I'm standing here and I have a pineapple and a banana, and you look at, actually you can probably do this, and you look at the shadow of me, can you tell that I'm holding a laser pointer? No. Can you tell that I'm holding a laser pointer now? So if you look at me from one side, you can see, you get some information about what I'm looking like. If I rotate, you get more information, and as I spin around, you get lots of information from my shadow about what I look like. This turns out is exactly how CAT scans work. So you start out with some light, you shine it on you, and this is an X-ray. This is your head, so it plays rounder than that. And this is a person, and this is an actual CAT scan. And so the person comes in, and there's generally a source and a detector across from it, that it'll measure the shadows, and it'll measure some absorption profile, how much your head absorbs, basically. And it'll measure it along some line through your head. It'll get information about, compressed information about one direction of your head. And then what they do is they don't spin you, because that'd be bad for sick people, I guess. But they have this round thing, and it just spins around. And so you spin around, not your head, like I said, and you work up actually information in 3D about your head. You get all these different slices, and if you add them up correctly, then you get information about your head. And this is what a CAT scan of somebody's head looks like. And you get this really nice, beautiful image just by sending X-rays through from lots of different angles. We're going to sort of do that, only unfortunately our way is more complicated because they were doing this many years ago. So now we have to do diffraction tomography. So we have two things that are different. Turns out X-rays, the wavelength of X-rays is very, very small, and your head is very large. That's good. I want to look at things that are sort of 1 to 2 microns big with light that has a wavelength of about 1/2 of a micron. So those are pretty close together. And so I'm going to show you some of the effects of that and what's going to happen with that. The other problem is your head absorbs light. Well, absorbs a lot of light, but X-rays can go through, but it still absorbs, and that's what we're looking at. We're looking at those profiles. This thing, here's a close-up of that. This does not absorb light. You can look through it. It looks clear. It's beautiful. This has hundreds and hundreds of waveguides in it, but you can't see them, which makes it harder. And another way to look at this is, so this is a crystal bowl. This doesn't absorb any light, but if I put this in front of my face, can you see me? You can see all sorts of really cool things. But what it does is it ends up scattering light. It bends light and it scatters light. This is also what diamonds do. This is why we like them, because they scatter light all over the place and they're pretty. That's why we like crystal things. So it turns out that things like waveguides, even though they don't absorb light, they do scatter light. So that'll be important. All right. So what happens? My students are cringing right now. When you take a laser and you send it through just an aperture, say just some sort of aperture that's sort of smallish compared to the wavelength. Now if this was an X-ray, all we'd see is we'd see black, light, and black. We'd just see shadows. Turns out that is not what happens. So what happens is you get all these weird sort of effects. So the physicists are excited about because this is all quantum mechanics. But I'm not going to write out the math. I'm going to show you pictures. But you get all sorts of really cool scattering. And so we don't have this bright, dark shadow thing. We have to get information out of the scattering. So it's a little bit harder to figure out. But there is a lot of information in this pattern. This particular aperture gives this pattern. It always does. So what would happen if I had an optical fiber that's, again, it's coming out of the board. It's very long, and I'm just looking at cross-section. And now it's an oval instead of a round thing, because that's more interesting. So I shine light on my optical fiber, and I look on a viewing screen. If I shine it through this end, I get a pattern on the viewing screen that looks like this. For all the math geeks in the room, this is a Fourier transform of a square function. It's called a sinc. But if I flip it, what if I flip the fiber, and I look at it from this direction? I get a very, very different scattering pattern. And so there's a lot of information in that. I'm actually looking at fibers that have this sort of ellipticity. And so these are very, very different things. There's a lot of information I can find out what these things look like just by sending light in and looking at what scatters. So I'm going to show you the same image here, but now for scattering instead of absorption. So this is now not your head. It's some optical fiber, probably. And it turns out that this scattering is related to the Fourier transform. So that scattering, now it's along an arc. Absorption goes in things that have absorption shadows go in straight lines. Light scatters kind of in circles. And so we actually measure on an arc. So as we spin this, and I look at lots of different angles, I can fill up data on this beautiful flower pattern in Fourier space. I really like that. And I can figure out, if I know what this scattered field looks like, I can figure out what I just scattered off of. So there's a lot of information there. All right. But unfortunately, I still have one more problem. I have lots of problems. So I said it was really weak. We don't have much of a density change. And if I send light into this very weak object, it kind of scatters a little bit. And you can't see any of it. So we need to get more signal in order to measure this. All right. So if this is a single object that I'm scattering, we'll say that I scatter off of one object and it looks like this. Cool. What if I put two of them next to each other? Well, they both scatter, but in addition to having this sort of overall pattern, I get this interference. Each of the scattering off of each of these interferes with each other, and I get this kind of rippling on and off. If I add lots of these together, what I get is this overall pattern with just little peaks along this pattern. But the really cool thing is here, instead of getting an amplitude, so a scattered intensity of 1, by just having 10 objects, I get 100 times more intensity. And that makes this thing really, really easy to measure. So what does that look like? I have a sample. I'm going to shine a laser through it. And this is my blue laser, because I think my blue laser is cooler. And this is what I see far away. So this is this exact sample that is up there too. And it looks completely empty if I look through it with a camera. And if I shine a laser through it, far away, I get this beautiful pattern of bright spots. And how bright these spots are and how quickly they diminish tells me exactly what that looks like. There's some math involved, obviously. So what do? We start with a laser. We put our sample. We see lots of bright spots. And we have a power meter here, so we measure how much power is in each one of them. And then we measure them all. And then we rotate it. And for each rotated angle, we measure the power. And so we build up this whole set of data about the scattering off of this object. So here's a sample. So what I did is I focused a beam into a sample, and I dragged it this way. I used very low power, so this is probably about 1 milliwatt. So this is about 1,000 times more power than I used. And I wrote fairly slow. And this, remember that pretty flower? This is all of my data in that space. So I then take that data, and I run some math, some inverse Fourier transforms on this to take all of my data and figure out what it was I started out with. And I get this picture. So this is now my waveguide. This is a waveguide that we wrote. It is sort of an oval, not a circle. And the index of refraction, the density, is constant coming out of the board again. We're just looking at the cross-section. So the light would be going into the board, and it would get trapped in this nice dense center. And you can see some cross-sections. It's pretty small. It's only a few microns in this direction. And it's about 100 microns big in this direction. The interesting parts about this are I now have resolution on the order of about 3 microns. And my index of refraction noise floor down here is about 1 times 10 to the minus 4. If you multiply those numbers and you tell a microscopist those, they usually just sort of go, you can't do that. But you can. We can measure things that are really, really weak with this method. So that's very cool. Now I'm going to make fun of the other guys, because you have to. So this is a picture of many of my waveguides. And again, I had to make many of them because I had to repeat them to get my scattering. So I've got many of my waveguides, and this is the exact same sample done with the state-of-the-art best microscope that I could find. This you can barely see with your eye. It's a whole bunch of noise when you do cross-sections. This has a huge amount of signal to noise. So we can really tell what we're doing and really get characterizations. It's quantitative. We can do 3 dimensions, which I'll show you in a minute. High signal to noise ratio. I have to write that for all the electrical engineers I usually talk to. Engineers want to know about signal and noise. This is qualitative. You can only do 2 dimensions, and you can't get a whole lot of signal out of it. All right, so I have a couple more pretty pictures, and then I'm really done. So I tried writing the other way. I focus the laser beam in the sample, and I drag it away, kind of like I told you I wrote the first time. Here's the writing powers and stuff. And here's my waveguide. So now this is the waveguide in length. So the light would now be traveling from here. It gets focused down. It gets trapped in the waveguide, and it travels down the waveguide. So now I've shown you the 3rd dimension, not just the cross-section. I can measure this in the other dimension as well, though it's continuous, so it's not exciting yet. To give you an idea of the scale, so this is in microns, and this is in millimeters. This is what it would look like to scale, this very long, narrow little wire. So this is my little optical wire, and we can make them very uniform, very nice. And here's a cross-section. Turns out round is better to match up with optical fibers, so this is a better result because we have nice round waveguides. really high signal to noise. These are very, very clear images. Now that we have this information, we've learned something about how the polymers work too. And so now we can start playing around a little bit. Like, what can we do next? So the next thing we did was we made something that wasn't uniform in length, because uniform is boring. So now this is, I've measured at certain points along its length, and I've taken cross sections which are round. So close to the laser here, I have a very high index of refraction, so very big density change. And then as I get farther and farther away from the laser, I get a lower index of refraction change. I get a lower density change. Turns out changing your waveguides along their length can change what the light looks like along its length. So this is good for optical circuits for connecting all sorts of different crazy things. So this is also a nice demonstration. These are just one-dimensional cross-sections here, because I thought it was a little bit clearer. You can see that the shape stays about the same, but the peak index, the peak density changes. So now we've learned how to make the waveguides. We've learned how to image the waveguides, and we've learned how to change them. So that's cool. And the last silly thing that we can do is, I say we can make circuits, not waveguides. Circuits are more fun. So here's a sample that actually has an optical fiber, a standard optical fiber they use for telecommunications to send internet around the world, embedded in our sample. And you can actually see there's red light coming through here into our waveguide. And here's a microscope picture. So this is an optical fiber, and this is the waveguide we wrote. And so we lined them up. We've shown that our alignment system works really well. We can take an optical fiber and write a waveguide off of it. We can get light into it. We can make all sorts of circuit things. We did one more cool little demonstration, which is fibers are cool, but I said black box, so we need more stuff. The first thing we did was we just embedded a mirror. So mirrors are good. We use mirrors all the time in optical tables. So we put a mirror in the sample, and we can make light bend in a 90-degree angle. It turns out that making light bend at 90 degrees does not seem like a hard thing, but in integrated optics, it's almost impossible. And so if you can't make light bend at 90 degrees and make little tight circuits, it's never going to be small. And it turns out fibers you have to bend in these big, giant circles, and so they end up being huge systems. So it's a silly thing. We just put a mirror in here, and we drew a little waveguide off of it and connected it, but it's actually a pretty big demonstration. All right, so I've done all of that. So at this point, I want to make the microscope better. So this is a standard microscope. We have light coming down. It focuses into a sample, and you need to look at a sample that's very thin. You've got a camera here. It's generally not quantitative. It is for absorption. You can do all sorts of really good things for absorption, but for index of refraction or density changes, they're not generally quantitative. And the resolution of this system depends on how small I can focus that laser beam. And that depends on the wavelength of the laser beam. It depends on very, very expensive lenses, and it depends on alignment. You have to have a really, really nice, precise system with good, expensive lenses to get a beam very small. I don't have to focus my beam. I can look through very thick samples, and my resolution is just as good. I can actually get resolution at about a half the wavelength of the laser. So this is a 500 nanometer laser, so I can get sort of hundreds of nanometers resolution in the system, so that's pretty small. So this is going to have a lot more applications just than looking at waveguides. So I'm going to start looking at more waveguides, playing around some more with the photopolymers, figuring out how the materials work. And then there's a lot of biological samples we can't look at these days without cutting up or killing, because you need to put them under a microscope. So if we could actually measure these things without having to cut them up, like big, thick samples, then that would be a lot of progress as well. So I'm starting to look into those sorts of things, and we're going to build this system this summer and play around with that and get that up and working and optimize it, and then see where else we can go with it. So I showed you lots of pretty pictures of waveguides and polymers, and I showed you we can make waveguides in these fancy materials, and I can measure them. So that's the wrong direction. Any questions?